Good day to you all. On behalf of Cenosco, it's my pleasure to welcome you on our 17th webinar about integrity management. My name is Luis, and I'll be facilitating the session today. In this webinar, we're going to look into the how to optimize your heat exchanger bundle inspection, going from a theory to a use case. What are the benefits on using and applying certain methodologies? Let's start first. Hi, Rowan. Good to see you again on these in this new webinar. So Rowan's is our pressure equipment integrity domain expert, right? So he's a chartered integrity material and corrosion engineer, or corrosion professional with over 12 years of experience. He's been with Cenosco for about 2 years now, right? But he brings a lot of experience from the field. There's a lot of training, a lot of the technical support here at Cenosco. Yeah.
Thank you,
How
Luis.
are you doing today?
Good. How are you?
Good. Thank you.
Good. Thank you, Luis. That was a really good introduction. So, hi, folks. Nice to meet you all. And let me also introduce Luis as well. If you have already logged into one of these webinars before, you must have known Luis. If you're logging in for the first time, here's a brief introduction. So, Luis is an engineer by background, a postgraduate degree in safety, has got an MBA to his name as well. But he typically comes from an oil and gas background with 18 years international experience in inspection and integrity management. With Cenosco, Luis is currently operating as a business development manager. And of course, he provides his expertise widely across the board as well. Thank you, Luis. Thanks for working with me on this.
Thank you. It was a pleasure to work on the content. It was a slightly longer content than usual, but I think we got a good output at the end. Good. Let's see what we're going to talk about. Let's see what is the structure for today. When you look at the agenda, we're going to talk about EVA. So for when you're talking about bundle inspections, for us it's a lot about the methodology to calculate and optimize that inspection that we call EVA. Right? We're going to look in a minute what does it mean in all details, but EVA means extreme value analysis. So we're going to talk about the theory, what it is, what is the benefit, why we've come with that methodology. Right? We can look into how to implement, what is the configuration, how to collect the data, how you analyze the result. We can look into a case study. Rowan prepared a case study where we took real data. We look into the outcome, right? So what does it mean to have the EVA implemented, looking into the benefits as well. We're going to close with some obvious conclusions. We can also talk a little bit what does it mean, where EVA fits in IMS. And we're going to finalize with the Q&A. But if during the call, during the webinar, we are live here, right? So if you have any question, you can type in the Q&A session on the chat that you have. If you also have any technical difficulties with refreshing your screen, I think typically if you refresh your browser, you should bring you back to the live session. Good. Let's get cracking then and see what is why do we need an EVA? Right? Let's introduce a little bit the concept. It's a methodology, right? That was introduced many years ago, developed together with the field inspectors, inspection engineer, domain experts. A big thank to Fred Hove was one of the brains and the heads behind the implementation and the development of those methodologies. When it comes to heat exchanger inspection, I think we can simply put it's a big and a dirty job, right? So it's one of those jobs that there's a lot of equipment handling, there's a lot of cleaning. It's a dirty, right? So you have to clean it, unplug it, you have to do an inspection, validate the result. And some of those exchangers can be quite large. We were discussing how big can an exchanger be, so we look into a typical 300 tubes, but 1,000, even 2,000 as a very large, 2,000 tubes, with 5 meters long, or even up to 5,000 tubes on a bundle. So it means that there's a lot of work. Typical low confidence, right, forces a lot of companies to do a full inspection, right? Inspecting 100% of the tubes. That means that depending on the size of that bundle, means a lot of inspection. We typically in EVA, we're going to talk a little bit later, that we use iris as a main inspection method with reliable outcome to do those calculations. I think we try to do some study cases with MFL, for example, but it gives a different kind of outcome. So we're looking here most of the time is looking at iris, even though sometimes it's the cleaning for required for an iris is it's bigger than another method. So we say time demanding for cleaning and inspecting. So we came and say, okay, if we want to do some estimates on how much we're going to save, we look into how many tubes we can inspect in a day. So I reach out to my former colleagues from SGS all the way back in 2004, restore some of my old inspection reports, the help of my friend Tadzio, that came up with some outcome and say, listen, we used to use as a reference for estimates at 300 tubes a day using iris, right? So 300 tubes in 12 hours, of course, be a little bit more or less, but that can give an idea on how much time is needed to do that task. So you can spend basically a crew of 2-3 inspectors on the bundle for 12 hours. So the EVA at the end will require less inspection, right? So we're going to take basically the worst case, the maximum loss, and we're going to apply that depending on the confidence. So that will save time, and we're going to show how we come on that calculation. So that's the EVA, where it comes from. So when we're talking about the EVA, right, it's an extreme value analysis. It's basically a statistical method to calculate the maximum wall loss. So it will look into one set of data. So it will look at the last inspection, and based on that last inspection and versus kind of the nominal, will define what is the maximum wall loss for the tubes that have been inspected, and say, is that a smaller representative sample? That's quite important as well. And we're going to look into the stratification, how to get to that good representation. Fitting on a distribution. So the process will have looking at the maximum wall loss, fitting the distribution. Can I apply the methodology? Can I extrapolate? We're going to predict the maximum wall loss over time as a corrosion rate, right? And I think what we are looking at, what is the remnant life, right? Or the main remaining life and the next inspection date. That's quite a good output to look after, say how long that equipment will last, and when is the safest point to inspect that equipment. Good.
And maybe to add on to your point, Luis, so one of the primary concepts here is to inspect a selection of your tubes from your tube bundles and trying to extrapolate your results across your wider tubes across your tube bundles. That is the primary concept here. And that is one of the reasons why extreme value analysis typically comes into use, because you're always dealing with maximas and minimas as part of that analysis.
Good. Thank you. So when you look at this, so now we've seen what it is, a bit of a high level methodology, but how does it work as a workflow? What are the steps? As any inspection, right? So it comes from that request to kind of plan an inspection, collect the data so you can set up your initial inspection. Say if it have never been inspected, say I want to inspect after a number of years. We're going to collect the data, wall thickness measurements coming from, or the wall loss coming from an iris and DT method. Technicality, define the stratification, right? Rowan is going to cover a little bit more the stratification, but it's a key element to define a reasonable sampling, right? Is that representative? And the stratification will play a big role on that. There's no point in just kind of inspecting a specific area of the exchanger. So we need to have a sample that represents the whole bundle. You're going to run the calculations, right? Define the stratification, run the calculation, evaluate the results. We're going to talk more in detail. What does it mean? But basically, is it a good fit? Not a good fit? You define a new certification, right? And then until you're satisfied with that, you go and finalize that calculation, right? We call calculation summary that we're going to come with the remnant life and next inspection date. At that point, we're going to use we call the horse race. Some people might have heard me talking about horse race. So here we're going to look into different ways to come up with the remnant life and the next inspection date. You can look at long corrosion rate, short corrosion rate, different kind of calculations. You're going to come with an EVA calculation, and you're going to come with a time-based approach. You're going to look at these three and say, what is the most conservative, basically, and which one you're going to apply, right? Once you get that calculation summary or the calculation up and running, you're going to get as an outcome a next inspection date. So in IMS, for example, that's going to be part of a schedule, right? The scheduling that's going to be used for planning the next inspection. But at that point, you already know, what is the sampling, what is the kind of tubes that you're going to inspect at the next inspection date. Did I cover everything, Rowan?
That was a good overview with regards to the workflow of the EV analysis. Yes,
okay.
Lewis, yeah.
So now I'm going to ask Rowan to go a bit more in details on the implementation, right? So how those calculations and those methodology works in a little bit more of detail.
Good. Okay. Thank you, Louise. So let's look into the implementation aspects, folks, because one of the primary aspect with regards to your implementation is to ensure that the data is collected appropriately. That is a key aspect, right? Okay. So with regards to performing a good quality analysis with regards to your tube bundles, we need to ensure that we have a sample representation and a homogeneous sample representation rather for your entire bundle. So if you look at the diagram on the bottom left, that is what we would call as a good homogeneous representative samples. As you could see, a selection of tubes have been marked for inspections. The ones highlighted red have been marked for inspections. And these are the locations, or these are the tubes that would be typically be inspected, and specific wall thickness results would be identified accordingly. The one on the right usually is not a very good representation. As you could see, majority of the locations where you would like to get wall thickness results are very concentrated at one location. So it's really not really representative of your entire tube bundles. One important primary aspect with the first step is to ensure that we have a homogeneous sample representation for your tube bundles. And here, as we know, we're typically interested in wall thickness results. So quantified results is what we're really interested in. And of course, the type of inspections also plays a key aspect as well. Higher the quality of your inspections with lower error margins usually will produce less conservative results. But however, at cases, if you incorporate lower quality inspections with higher margin of errors, in such cases, your results will be quite conservative. So you also need to take that into account. And usually, the recommendation is to at least select about 20 to 25% of the tubes per stratum. So what does stratum mean? So in one of the previous slides that Luis covered, the workflow for your EVA, the stratification is an important aspect with regards to this analysis. So you would like to group tubes similarly, depending upon the conditions it typically sees. So in some cases, the inlet side and the outlet side can be two separate stratums, because an increase in temperatures can increase your corrosion rates on the outlet sides, just for example. So in such cases, your inlet and your outlet could potentially be part of two specific or two separate stratums. If that is not the case, you can just class your entire heat exchanger bundle as one specific stratum. But as long as your coverage is spread enough, as long as you have a good understanding with an overall coverage, that is a good starting point with regards to data collections. You really do not want to be focusing on specific locations and not focusing on other locations where you do not have any information or data. So the key part here is to ensure that we have a good representative sample of your entire heat exchanger bundles. Okay, so that is typically step one, data collection and stratification. Step two is all about assessing the goodness of fit. What is the quality of the data and how does it fit within our distribution? Because as Lewis has highlighted several times by now, EVA, extreme value analysis, we typically look at maximus and minimus. So all of us, maybe we should all be familiar with normal distribution, where we work with mean, average. But here, with regards to extreme value analysis, we're looking at extreme values. That's why we're primarily dealing with maximum values. In such cases, we're typically dealing with a distribution called distribution plot, such as Gumbel distribution. And we're typically assessing our data and ensuring the wall thickness results that we have received is a good fit with regards to a Gumbel distribution. And in order to perform this assessment, there are a number of methods available, a number of statistical methods available, KS, Kolmogorov-Smirnov, Anderson-Darling statistical methods, typically assesses the quality of the fit, ensures that the data that we have received typically fits the distribution quite effectively. And in some of the statistic methods, a lot of emphasis is actually put towards the fit quality of the tail. When it comes to distribution and looking at the goodness of fit, the fit quality of the tail is quite important as well. And apart from that, there are a number of graphical methods: probability plot, quantile plot, exceedance plot. So from the graphical methods, we can also have a look to understand how our results typically fit within our distribution plots. So usually the recommendation is to use a combination of these methods, statistical methods and graphical methods combined, and make a decision to see if we have a goodness of fit data. And if there's no goodness of if there's no sufficient goodness for fit data, what do? We just revisit, go back, just see if we have to stratify a tube into multiple stratums and so on. Okay, so before using or perform the EV analysis, we need to also, from an assessment perspective, we also should be aware with regards to the conditions, with regards to the corrosion behavior. That is an added advantage. So understanding how the systems operate, understanding the corrosion behavior also helps us to perform a robust analysis as well.
And again, the goodness of fit, I mean, if it's not a good fit, you can basically just remove the outcome of that calculation, right? Mm-hmm. Or you do. Question is, would you do more inspection and run the calculation again until you reach that, representation, or just drop the calculation?
No, good question. So one aspect that could be done is to review your data, understand why there is no goodness for fit data. There could be cases where some of your tubes are corroding at a very high corrosion rate, some are not. So it is typically identify such cases. And if that is the case, you might want to identify those bad actor tubes, and you want to stratify them, group them as a separate stratum. So in such cases, we will have one or multiple stratums, and you would do an EV analysis per stratum level.
Yep. Good, thank you.
Okay. And that is typically step number 2. Step number 1 was collecting data, stratifying your data. Step number 2 was assessing the goodness for fit. The third step is extrapolating the results. So if you look at step number 1, we did not opt for a full 100% wall thickness results for our entire tube bundle. We opted for a homogeneous representation of inspections. So what we're trying to do is, based on our results, we're trying to extrapolate the results across our entire tube bundles. So in this step, what we're trying to achieve is to statistically infer the maximum wall loss for the entire heat exchangers. And again, a couple of statistical methods are typically highlighted: return level, extrapolated distribution level. Let's look at extrapolated distribution level in this case. Later in the case study, we can look at the return level as well. So whenever we're dealing with extrapolating results, where we're trying to identify the maximum wall loss, we typically include it along with confidence bounds as well. So as you could see from the chart further below, extrapolated distribution plot, the peak of the plot is your most likely wall loss. So in this case, the most likely wall loss is somewhere about 0.657, and the maximum wall loss at 95% confidence bound, which is highlighted in red, is 1.002 millimeter. What does it mean by maximum wall loss with 95% confidence bound? It typically means that 95% of your wall thicknesses are below 1.02. If you're looking at 99% confidence bounds, then your maximum wall loss will potentially be higher as well, maybe 1.1, 1.15, for example. So what it really means is that 99% of your results would be lesser than that respective value accordingly. Okay, so when it comes to extrapolating results, it is also important to combine it with the level of confidence bounds that you're working with as well.
It's just a quick one. Like I mentioned, we do have some other, methods and methodology that we use to extrapolate the results. Also in IMS, we do have some other distributions that we analyze the corrosion rate, right? And then we have the same confidence and say, like some of these Weibo distributions, and say,
Yes.
we look at the corrosion rate, but in this case, that's the maximum wall loss, right? So on that wall loss, we calculate the remnant line.
Okay. Okay, so now let's look at how extreme value analysis typically sits in this hierarchy. How does it sit inside the specific framework? Luis, you want to take over?
Yeah. That's my favorite diagram. So we wanted to bring a bit in the context, right? So the EVA for us is not a standalone application, right? That you have that you run whenever you do an inspection. It's part of an integrity management system, right? So those calculations will be tied up to an equipment, right? So we look into the asset hierarchy as it comes from a CMMS application like SAP and Maximo, right? So we're going to look into the site plant unit, functional location, and the equipment. At the equipment level, we have the circuits, what we call circuits, right? So the circuits is the place in IMS where we're going to look into corrosion calculations, right? Looking into an age-related failure mode, right? So thinning, so it degrades over time. So how you do that? So in the circuit, we're going to look into how corrosion, how thinning happens on, piping, on vessels, on columns. And in this case, we have a methodology called EVA that will look into the bundles specifically. We had another methodology called SIDAP, for example, that will look primarily on the piping side. Again, another statistical model. So that circuit, that's the place of the EVA, right? At the same time, you can also look into the RBI components, right? So we're looking at the holistic view, say how your corrosion behaving, but you do a risk assessment, right? So you look at the criticality, you're looking at your confidence rating, right? You're going to look at your barrier management system, right? You're going to come as an interval factor out of that RBI, and that interval factor will be used in the calculations, in the circuit calculation. So it's really integrated. So it's not only about looking at EVA, but it is also looking to RBI analysis, right? So on a bigger picture, the outcome of that calculation will be pushed or will be used in what we call schedules. Schedules are synced with the work orders and so on, right? So that's a planning side. At that planning stage, you can also defer inspections. You can group them for planned event, yeah. And then you're going to run the cycle through an equipment condition history and receiving the data back, and then you're ready to calculate again. So it's a whole loop. So I just wanted to kind of, show that it fits on the overall integrity management approach. It's one of the tools, one of the calculations that we can use to manage the bundles. Good. Anything to add?
Yeah, I mean, EVA sits quite well under the circuits because just like what Louis highlighted, the way we treat tube inspection is that every single tube is a specific CML, and we would typically record wall thickness on a CML level, on a tube level. And once we have results, and usually for a tube bundle in this case, we will be inspecting a representative sample, 20%, for example. And once we have those wall thickness results clearly quantified, we can just update and we can just project and extrapolate these results for your entire heat exchanger bundle. So yeah,
good. Let's look into the use case. I think we maybe run a bit behind, but let's look into the case study that Rowan prepared and with actual data.
Okay. Yeah, this is an interesting case study, folks. So let's spend a bit of a time with regards to what the background is before jumping on to the actual data and what the outcomes were. So the background here is that we will be looking at the wall thickness results for a crude preheater. The crude preheater had roughly about 120 tubes constructed of carbon steel material. And the crude preheater is typically operational along with two other similar preheater trains. But the case study that we're looking at will be for one specific heat exchanger, but the other two heat exchangers in the other trains were also inspected, and we typically had comparable results out here as well. And also worth to also highlight the philosophy of the customer in this case. So these heat exchangers have been in operation close to 25 years. That is typically the design life of the equipment. And all these equipment were typically reaching the end of its design life. And the customer typically wanted to extend the life of their asset by another 10 years at least. So in this case, historically, what had been done with regards to these heat exchanger bundles is that at specific intervals, boroscope inspections have been done with regards to assess the tube internal conditions. In some cases, boroscope is used also from the shell to assess whatever is available or whatever is visible with regards to the tube external conditions as well. Again, a number of boroscope inspections were done, and the customer had some understanding with regards to where issues were, potential issues. But again, these were just very qualitative data. We could not quantify what was the wall thicknesses, what was minimum remaining thicknesses, and so on. So just like I said, the intention here was for the asset to extend the life of their equipment by another 10 years. So again, if this approach was not done, if inspections and a follow-up analysis had not been done, the likely course of action here would have been to just replace all these bundles and just move on to operate for another 10 years. But of course, the customers wanted to also understand if replacements were actually required. Is it even necessary in certain cases? So 1 year prior to the life extension project, that is when a plant shutdown was taken, and these three heat exchangers were typically inspected to understand the conditions and so on. And again, there were limitations with times and resources. So the intention was to inspect a specific sample of tubes, a representative sample, and then make an estimation with regards to what could be the potential maximum wall losses, and then make a decision to see if we are safe to operate for another 10 years. Okay, so in this case, like I said, 120 tubes were there in total. 23 tubes were inspected. Inspection was done in 2023. And based on the boroscope inspections, there were some understanding with regards to where the issues were. So a number of tubes that were known to have issues were selected for inspections. And as you could see on the right, in the center right, a selection of tubes have been selected. And as you could see, it's a very good homogeneous representation as well.
So just bringing maybe a question that from later on, there was a question about is it appropriate to inspect 100% of the tubes to establish the baseline data? Would you think would you say that the full inspection would be good at the beginning, or since the first inspection applying the methodology can reduce that 100% baseline?
No, usually what sites tend to do is that they would do a full 100% inspection as a baseline, and then following that, a representative sample, 20-25% is usually chosen, and based on that, an assessment is made and future inspections. Another 25% is typically chosen, and your remnant life and your next inspection dates are typically identified. But in this case, like I said, there were constraints with times and resources, so 100% inspection was not really ideal for all parties. So that was typically your first step, just what we have highlighted earlier. The second step was to assess your wall thickness results and identifying if the results were of a good fit. Because if we were getting contrasting results with wall thickness results, maximum wall losses, then ideally this goodness of fit would have really highlighted such cases. For example, we have inspected 23 tubes. If about 5 tubes were corroding at a very high corrosion rate and the remaining 18 tubes were corroding at a much lower rate, that would have been evident with regards to the goodness of fit data as well. So here, the KS and AD methods were used. And based on that, along with the graphical methods, the quantile method, the probability method, where we would typically review the plots and assess how good the fit quality is. And based on that, it was really evident that the goodness of fit data was quite good as well. If you go back to the previous slide, I've just got one more thing to highlight there. So on the previous slide, just at the bottom, I don't know if you all could see, there's a histogram present that typically highlights what the outcomes were from the result from the inspections. So about 65% of the tubes had wall thickness results, minimum remaining wall thickness results from around 1.8 to 2.1, and about 35% of the tubes were around 2.1 to 2.4. So as you could see, almost all the inspected tubes were within a specific range. The inspection results were not chaotic. It wasn't like everywhere. So it was still very focused on a specific range and so on. Okay, so yeah, goodness of fit, we've covered that. And the next one would be to extrapolate your results as well. So what we have done right now is inspect about 20% of the tubes. Now we'll be extrapolating that to identify what the maximum wall losses for different confidence bounds. So in this case, a written level method was used. And as you could see, the most likely wall losses were around the region of 0.816. However, different confidence bounds were applied. So if you look at the small grid at the top, that will typically highlight what your wall thickness results were for different confidence bounds. So at 99% confidence bound, the maximum wall loss expected is about 1.059 millimeter. With about 80% confidence bound, the expected maximum wall loss is about 0.937 millimeters. So, of course, 90%, 95% confidence bounds could also be used, and you will have specific results. But the thing that I would like to highlight here is that higher your confidence bounds are, the more conservative your results are as well. So in this case, the client typically opted to use an 80% confidence bound. It's because there were a number of qualitative inspections done in the past, a number of boroscope inspections, and that was revalidated using iris inspection in 2023. And a good understanding of their wall thickness results were typically identified. And it also typically validated this thesis as well, because historically they had some level of qualitative data. And on quantifying these data in 2023, they did not expect something out of the blue as well. So that was a good finding with regards to with regards to the inspection that was carried out. So next, we can have a look into the results with various confidence bounds, because so far we have identified the maximum wall losses. But of course, ideally, we need to understand what is my remnant life, what is my maximum inspection interval. Just like I highlighted earlier, a confidence interval or confidence bound of 80% was used. And based on that, an estimated remnant life of about 9.5 years was identified. Like I said, the customers was planning to extend the life of their asset by another 10 years. However, we also indicated that with a remnant life of 9.5 years, applying the industry standard half-life concept, an inspection had to be carried out every 4.5 years or 5 years accordingly as well. So that gave the customers much more assurance with regards to what they are dealing with. So instead of having to replace everything, which was like their baseline option, they were much more confident with regards to what needed to be carried out with regards to the outputs. And let's look at the learnings and summaries from this case study. It's a good case study with regards to how this had developed over a period of time. So let's look into the benefits or the findings which stood out as highlights from this case study.
Lewis? Yeah. So I think the first point that we get is the duration of the inspection and the preparation, right? So we're reviewing a few processes on how you coordinate, on how you run the field inspection. So we noticed like a reduction, about 40%. Of course, you're not going to get the 40%, year after year, but from that baseline, you can consider kind of more over 40% reduction on the inspection cost, right? So here we're talking a purely office kind of preparation work and less inspection time in the field, both of them, right? That also leads into the reduction on the duration of the turnaround, which means that the equipment needs to be open for less time, right? So it means you can close it faster, you can release and commission and start the startup again within a shorter interval. So we noticed that 12% duration, again, it's a direct impact on the inspection time into the uptime. So you basically, spend less time.
And one thing to highlight is that these exchangers were part of the critical path of the project. So that's why, just like what Lewis had highlighted, since it took less time for inspections, they were able to close out the channel head quite quickly, and they were able to restart production faster than expected.
And finally, I think the 85% on estimated savings as an outcome. We talked a lot about that and say, how can we look into the impact on risk, right? So it's not going to be about risk reduction, but it's more like understanding the risk, understanding the threats, and how the equipment is degrading. And at the end, what is the impact on the replacement of that equipment? Like Rowan said, in this case, they avoided basically a replacement of that exchanger earlier than needed, right? So there's a long process of buying a new equipment and replacing. So with that methodology, it managed not only to reduce the time and the turnaround, but also preventing some of these costs, such as either repair or replacement. Now we have a better understanding on both risk and remnant life. So you have a much better grip on what is the actual condition or health of that asset, right?
Yeah, definitely. So the remnant life, just like what we highlighted, we're closer to 10 years. But if at all your corrosion rates were bound to increase, there were other operational mitigation actions kind of identified. It was a crude preheater, so the injecting corrosion inhibitors to reduce your expected corrosion rates that could lead to longer remnant lives and things like that. So of course there were other potential actions that was in the back of the customer's mind, but overall that was a lot more better than completely replacing the bundles. Now the customers had much more control with regards to what they were dealing with, the risk and the threats.
Thank you. So this is kind of the benefit on that use case, but in an overall, when you look at the main conclusion, what are the benefits of applying a methodology like that? So I think it was quite clear on the inspection and maintenance and the cleaning time required for that. We know that many times iris require a better cleaning than other methodologies, but I think that pays off if you're able to use the EVA methodology. Right? That representative sample that we take brings some of these can be conservative in a way, right? Ensures inspections are carried out on appropriate intervals. Appropriate intervals means an interval that you understand where he comes from, that you look into your criticality, the confidence, the confidence interval, and that interval is the most optimal interval you can get. And I think like Rowan come up with that conclusion. I think it sounds really well that EVA ensures an adequate yet confident inspection. I think it kind of wrap up, look into the quantity, how to quantify those gains. You can take the percentage that from that use case, but I think it reflects quite well the benefits of a methodology like this.
Definitely.
Good. I think we are spot on time. We have some time for Q&A, right? So we got some questions from the registrations. Still see we have almost 80 people still connected. Thank you for that. So I'll bring some of the questions that we selected from previous registrations and from today. We already answered the first, right? First question, how do we measure the tube wall thickness exactly? In this case, we talked a lot about the iris methodology, right? It's an inspection method. It's an NDT. It's a non-destructive testing method that requires you to clean. So you introduce a probe filled with water to work as a couplant. So you're going to take the measurements along the tube, and the machine will record the maximum wall loss for that tube. And that we use as a measurement to define the maximum wall loss per tube. There's other inspection methods that can be used, like such as an MFL, that will require, will require less cleaning, but it will also be a less accurate, maybe not a good fit for this methodology. Right, Rowan?
Yeah, I would agree. So, simple concepts like high quality inspections, you have much more confidence with your results. The error margins are low. Less conservative, your results are. Low quality inspections, you do not have enough confidence with regards to your inspection techniques. Error margins potentially could be much more higher. So more conservative your results are.
So on a follow-up, so we talked about, is it appropriate to inspect 100% of the tubes to establish the baseline? I think we said yes as a baseline. But then maybe on the next to say, how do you do the selection? So the question is like, is a selection of tubes based on experience or a specific published document?
Yeah, I don't think there's specific published documents available to highlight which specific tube has to be inspected. It typically deals with what you're dealing with, like what are the products that you're dealing with and so on. And usually the selection typically comes from selecting a representative sample, because all the tubes will have similar configurations. So you might want to ensure that your selection is kind of spread out to start out with if you're inspecting a sample. So yeah, that would be a good start.
And I think over time, right? So if you do your baseline 100%, and then the next time you want to do a representation, right? You can take your experience, and then on the next inspection, you can select, oh, let me repeat an inspection on the tubes that had the maximum wall loss, but I'm also inspect the tubes that were not inspected before. So IMS will give you some guidance, right, as a measurement set configurator on which tubes are better to select. But so that's going to be a lot, I would say, on the experience, right, on how to get that.
Agree. Once you gather some level of information, the experience, of course, will play a part. You would typically, or you will have data that kind of validates where the issues are. So in some cases, you would want to revisit. In other cases, you would want to extend your coverage to other tubes that have not been inspected for a certain duration of time.
Interesting question that came up. I think can we apply EVA to assess tank floors? I think
Um,
we haven't discussed that, but I think it's yeah, you could apply concepts, but the EVA exactly was done, to use iris as a tube, because not the typically the floor are going to use an MFL,
exactly.
so you don't get the same precision as a wall thickness as a
Yeah,
measurement.
yeah. No, EBA with tube bundles is primarily used because you're mostly, or in some cases, you are inspecting a representative sample, but you don't really know what the conditions of the other tubes the same bundle are. For tank floors, I don't think that would be the case. You cannot just take a sample inspection from a certain section of the floor and just like extrapolate the results. One other area where EBA is being explored is items and similar services. Again, it's very similar concept. There could be multiple equipment and under similar services. Could we do an inspection in one location and try to extrapolate those results across other equipment and similar services?
But in short, right, EVA is a tool that is built in IMS. In IMS, it's not possible because the EVA calculation is only available for the equipment type, exchanger, and bundles. So it's a very quick, straightforward question, and say if you want to explore the methodology for other things, I think it needs a bit more investigation. Yeah. What is the purpose of stratification? I think we talked about that. Is kind of to come up with the true sample, or a true representative sample of that exchanger, right? So you group your tubes in a way that represents the corrosion. And so basically, tubes that suffer from a similar degradation, like Ron said, oh, the outlet has a similar temperature, right? So you expect a similar corrosion rate rather than the colder surface on the top side.
Yep, agree with that.
Yep.
Yep, yep.
Okay.
So one tube bundle can have multiple stratifications or stratums, and you would typically perform an analysis on a stratum level. So one tube bundle can have, let's say, two stratums. You do an analysis on stratum 1, you do an analysis on stratum 2, and the worst affected results are typically applied to your heat exchangers, and your inspections are typically carried out in accordance.
So it's already answered one of the questions to say, if we have multiple stratifications with different results, how your inspection planning is affected. So exactly what Rowan said, we're going to take the worst case, right? It's part of IMS life as a horse race. Take the worst case and apply that for the bundle. We got that. We are really running out of time. Can we apply this methodology on air coolers? I think it's a straightforward answer. Yes.
Yes.
You can apply that. I think one of other examples that we took was also related to air coolers, but heat exchanger bundles in general. Another quite interesting question is, how can EVA help with assessing RBI and plan future inspection in accordance to the risk? You have a minute.
Yeah, sure. I'll pick this up. So, of course, RBI is a much more detailed technical assessment. We take into account your criticalities, which is a combinations of your probabilities and your consequences. So in order to assess your probabilities, you're mostly interested in your corrosion rates and so on. So EVA can allow you or give you the projected estimated corrosion rates to be used in your RBI. Similarly, for your remnant life calculations within your RBI process as well, which kind of sits within your probability. Also, another important aspect within your RBI is your confidences, how confident you are with your inspections. And of course, your inspection techniques play a part with that. How robustly are you monitoring specific parameters that affects your degradation? It also plays a part in that as well. So as part of that, yes, you can typically incorporate EVA results, run an RBI assessment, and ultimately you will have the outcome from your RBI, which can allow you to potentially increase your interval factors. So in this case study that we saw, we went with a default interval factor of 0.5 half-life. But if you do a robust RBI assessment, that 0.5 could be increased if your criticalities are lower, or that 0.5 could be reduced if your criticalities are higher.
Good. Thank you. I think we're really running out. Thank you guys for watching. There's a small question here. Histogram seemed difficult. The graphs are difficult to analyze. Of course, methodology comes with the training, right? So thank you for Owen to participate in the content. For the viewers for watching, you had quite a good audience until the end. Thank you for your time. The webinar will be soon available for download from our website. Our marketing team will follow. And then before we go, I'd like to mention that we're already planning our next IMS webinar. That's going to be in October, right? Thank you, guys, and see you next time.
Thank you, folks. Thank you, Luis.
Thank you.